So today we're going to talk about simplifying radical expressions. We're going to spend several days on this. So radical expressions are expressions with a radical sign, and we're going to simplify them as far as we can. And here's the first thing we know. If we have the square root of a times b, that's equal to the square root of a times the square root of b. So you can break it down into factors of whatever that number is and take the square root of each one. So we'll be looking for perfect squares. So again, think of the numbers that are perfect squares. 1 squared is 1. 2 squared is 4, 9, 16, 25. So you need to become familiar with the perfect squares. At least less than 100, I would imagine. 64, 81, 100. So those are all perfect squares. So you'll be better if you can think of perfect squares. So in looking at the square root of 12, I want to break it down into probably the square root of 4 times 3, because 4 is a perfect square. Then using this, I'm going to break this down into square root of 4 times the square root of 3, and I can take the square root of 4, that would be 2 times the square root of 3. So that would now be simplified. So that's what you're looking for, perfect squares. And if you can't find them, you can always make a factor tree and write it in exponent form, and you can find squares that way. So 90, hopefully 1 pops into your mind, 9 times 10. And again, sometimes you'll have more than one perfect square, like if 10 had a perfect square and we could factor it farther. I'll break this down into the square root of 9, and eventually you'll leave out some of these steps, probably this step, and then go to your answer. Square root of 9 is 3, so we have 3 times the square root of 10. Now we can use that rule in reverse. If we have the square root of 3 times the square root of 15, that's the same as putting it underneath one radical, the square root of 3 times 15. Now you can think of it as the square root of 45, or you could break 15 down and think of it as the square root of 3 times 5, and here then you see that 3 is squared. So, or you can just think 45 and break it down, but since 45 is a small number, that's easy. If you had bigger numbers, you might not want to do that. So what are we going to find here? The square, I'm going to leave a step out. The square root of 3 squared is 3 times the square root of 5. So we might not have to put it under a radical sign every time, then we can kind of break it down into that. Square root of 72. Now most of you, when you think of 72, are going to think 9 times 8, which is fine. Square root of 9 is 3, so I'm going to take the 3 out. Again, I'm kind of leaving out that in-between step now, so if you still feel like you need to take it, that step, fine. But are there any perfect squares in 8? Yes. We can break that into 4 times 2. So this would be 3 times the square root of 4. I'm putting this step in again, you don't have to. Square root of 4 is 2, so it becomes 3 times 2, which is 6 times the square root of 2. And again, I'm leaving a couple of steps out there, so if you need more steps, that's fine. Alright, so again, you might want to either think of this as the square root of 48, or the square root of 10 times 24, and let's see if we can find some perfect squares in 24. It is what? 4 times 6. So 4 would be a perfect square, so if I take that out, I'm going to be 2 times the square root of 2 times 6 is 12. And then I can think of 2 times 4 times 3 is 12. Square root of 4 is 2. I bring that out and take it times the 2, so I get 2 times 2 times the square root of 3, which is 4 times the square root of 3. And again, I'm leaving a couple of steps out. You might need to put those steps in here at the beginning, I don't know. Alright, so now we want to find the square root of some things with variables in them. So again, think of your numbers first. Are there any perfect squares in 40? Well, yes, 4 times 10. X to the 4th is a perfect square. Y to the 5th is not, so we can break it down into y to the 4th times y. And z squared is a perfect square. So now I'm going to just take the square of all my perfect squares. Square root of 4 is 2. Square root of x to the 4th is x to the 2nd. Square root of y to the 4th is y to the 2nd. Square root of z to the 2nd is z. And what do I have left? I have 10y. And again, when you think you're done, look at what you have there and say, are there any perfect squares in 10 or y? Well, no, they're not, so I'm done. And this one, again, let's break it down. 45 is 9 times 5. A to the 4th is a perfect square. B to the 5th would be b to the 4th times b. And then c to the 6th. So, square root of 9 is 3. Square root of a to the 4th is a to the 2nd. Square root of b to the 4th is b to the 2nd. Square root of c to the 6th is c to the 3rd. times the square root of, what's left? 5b. Now, we haven't talked about this yet, and I don't have this in your slide, but technically you're supposed to have c to the third in absolute value. I'm not so picky on that. I don't think I'll have you do that on your homework, but I do at least want to mention it to you. And so you don't have it in the next slide on your work, but I have it in my slide, I think. I added it. And so this statement says, for radical expressions where the exponent of the variable inside the radical is even, and the exponent, once you simplify it, is odd, you must use absolute value. So we're going to put absolute value symbols around it if you want. I'm not going to count wrong if you don't, to ensure non-negative results. So here, the absolute value of x squared, that's even, but when you take its absolute value, you get an odd exponent, which is 1. You're supposed to use the absolute value. Again, like I said, I don't really do that. X to the third, well, you think of that then, that's not an even number, so you don't have to worry about it there. X to the sixth, you would think of x to the third, that's odd, so it'd be an absolute value. But I'm not going to be too picky on that, so if you don't do that, I'm not going to count them wrong. I just want you to be aware.